So here we're going to solve a non-homogeneous second order differential equation. So it's non-homogeneous because we have some function, something other than 0 on the right hand side of the equals, and it's second order because we have the second differential here. We've been given the initial conditions that when t is 0, theta is 2.4 and d theta by dt is 2.9. So the next step is to form the auxiliary equation. So we look at the coefficients on the left and we put those into a quadratic. So we've got 1 times m squared, 6 times m, and then 9 on the end. And those we set equal to 0. This particular one we'll factorise, and we get m plus 3 all squared equals 0. So that means m is equal to negative 3, and it's a repeated root. So this means that the complementary function will take the form of a plus bt multiplied by e to the negative 3t, and it's negative 3t because we've got a negative 3 here. Now, because we have a non-zero on the right hand side, we have to think about a particular integral. And because the right hand side of the equation is 13.7, which is a constant, then we choose our particular integral to mimic that form. So this is a constant, so we'll choose our particular integral to be theta equal to k, some other constant, which we don't yet know the value of. And now what we do is we differentiate this thing twice. So this tells us that d theta by dt, if we differentiate a constant, that's equal to 0. And if we differentiate again, then the second differential is also going to be equal to 0. So we take these three things and we substitute those back into the original question. And if we do that, we end up with all of this stuff on the left. So 0 plus 9k equals 13.7. We rearrange that and we find that k is equal to 1.522. So we've just worked out the complementary function and we found the value of k, which is our particular integral. So the next thing is to remember that let's just move that out of the way, is that the general solution is found by adding the complementary function and the particular integral. So therefore theta, the general solution, is the complementary function plus the value of k that we just worked out. But we need to find the particular solution, and we do that using the initial conditions that we were given earlier, but I've just repeated here. And so what we do in the first instance is we plug this one and this one into here, into the general solution. If we do that, we can work out the value of a. And then if we go back to this and differentiate it once, we can then put the value for t and the value for d theta by dt in. And that allows us, and also the value for a that we just worked out, and that allows us to work out the value for b. And then finally we put a and b into our general solution and find that the particular solution is the equation given here.